All right, so what about magnetic forces on moving charged particles? Well, let's get to it. A moving charge is going to be deflected when it crosses magnetic field lines, but not when it travels parallel to the field lines. Here we have a picture of a magnet. Remember, the magnetic field goes from north to south. Right? So north to south is our magnetic field. That's the direction. It's going to be in this way. Notice the arrow is pointing in the same direction. It's a three-dimensional picture, so I want you to see what's happening. All right? And the beam of the electrons are coming this way into the magnetic field. And then they end up turning this way to the left. How does that happen? If a charged particle moves in a magnetic field, the charged particle experiences a deflecting force. This force is greatest when the particle moves in a direction perpendicular to the magnetic field lines. At other angles, the force will be less. The force becomes zero when the particle moves parallel to the field lines. So I've talked about the first two right-hand rules. We have a third right-hand rule, which is a little bit more difficult, and in standard physics, we don't have to worry about it too much. More advanced physics will use it, but let me at least go through it quickly here. All right, so the way this works is we have three variables that are interacting. We have a force, the magnetic force. We have the current, because electrons moving in a line is going to be a current. And we also have the magnetic field. So all three of these are vectors, and they're acting all perpendicular to each other. So if you may have seen this little thing here at some point in math class, the XY plane and then the Z plane. The Z would be coming out of the page. This is the same shape. So we start with the XY, and then we have the middle finger going that way. Forgive the crudeness, but this is the easy way to remember it. F is represented by your middle finger. B is represented by your pointer. B, remember, is the magnetic field. And your thumb is the current, the direction of the current. So FBI, like the agency. F, because that's easy to remember, right? And then BI. Let's try it. So let's figure out what direction is the force acting as this electron beam travels through the magnetic field. I've got my FBI right here, right? Now I just have to orient it in a way that is comfortable, natural. So we have the electron beam going this way. Okay. I have my magnetic field, B, from north to south. Okay. There we go. That's where I'm at now. And then my force is pointed up, just like it shows in this diagram. Okay, so this little hand trick allows you to be able to predict how particles are going to move, how forces are acting, or what direction they're acting. So this works if it's all perpendicular. But if it's not perpendicular, then we have to use a little bit of trigonometry to figure out what is the perpendicular component of the force. The direction of the force is always perpendicular to both the magnetic field lines and the velocity of the charged particle. The deflecting force is different from other forces, like the force of gravity between masses, the electrostatic force between charges, and the force between magnetic poles. The force acts on moving charged particles. The force that acts on moving charged particles acts perpendicular to both the field and the electron's velocity. Deflection of charged particles by magnetic fields provides a TV picture. At least it used to. TVs don't have those big backs anymore. When they had those big fat backs, they were CRT TVs or CRT monitors. Maybe you've seen some of them if you're into gaming. Those are better because you don't get as much lag. But a CRT monitor, for example, that CRT stands for cathode ray tube. And what a cathode ray tube is, very simplistically, is a tube where you have a beam of electrons coming through it, and you have a strong magnet. And those electrons come through, and in the presence of that strong magnet, they become deflected. And depending on the speed that you're sending those electrons, they're deflected at different angles, allowing for pictures to be shown on a screen. Charged particles from outer space are deflected by Earth's magnetic field, which reduces the intensity of cosmic radiation. So that's where you get pictures like this, the aurora borealis, northern lights. You can see the movement there. That's the particles interacting with Earth's magnetic field. That shield protects us from harmful radiation getting to Earth's surface and affecting the residents here. A much greater reduction in intensity comes from the absorption of cosmic rays in the atmosphere. So the atmosphere is also absorbing some of these cosmic rays to also help protect us. So by now, you should be able to answer what happens when a charged particle moves in a magnetic field.